Hello everyone, welcome to my YouTube channel. Today I'm solving Leetcode question 430. Flatten a multi-level doubly linked list. You are given a doubly linked list which contains nodes that have a next pointer, a previous pointer, and additional child pointer. So definition of our node is shown here. So we have a class node, and then we have the value, and then we have the previous pointer points to the previous node, next pointer points to the next node, and then child pointer points to the child node. This child pointer may or may not point to a separate doubly linked list, also containing these special nodes. This child list may have one or more children of their own, and so on, to produce a multi-level data structure as shown in the example below. Given the head of the first level of the list, flatten the list so that all the nodes appear in a single level, doubly linked list. Let current be a node with a child list. The nodes in the child list should appear after current node and then before the current node's next node in the flattened list. Return the head of the flattened list. The nodes in the list must have all of their child pointers set to null. Take a look at example 1. So we have a 3-level doubly linked list. So the first level, we have 1, 2, 3, 4, 5, 6. And then for the second level, we have node 7. 7 is 3's child. And then also in the same level, we have 7 point to 8 as next node, 9, 10. And then in the third level, we have node 11 and 12. Node 11 is node 8's child node. So to return a single level doubly linked list, when the flattened list is starting from 1, goes to 2, goes to 3, and then node 3 has a child node, that's node 7. So following the rule, the nodes in the child list should appear after current node and before current node's the next node in the flattened list. So in that case, 3 point to 7, so we should, in the flattened list, 7 should appear after 3. And then for this 7, we should also first visit all the adjacent nodes and also the child nodes before we backtracking to the previous level, which is the first level, the same level as the node 3. So in that case, from node 3, we go to node 7. From node 7, we go to node 8. And node 8 has the child node, that's node 11. So following that rule, we should go to node 11 first, and then visit node 12, and then backtracking after finishing visit all the nodes in this child list. So in that case, after finishing visit node 12, we backtrack to visit node 9 and node 10, and then after finish visiting all the nodes in this second level, we backtrack and return to the previous level, which is the first level, and then visit node 4, 5, 6. That's why the output is 1, 2, 3, 7, 8, 11, 12, 9, 10, and then 4, 5, 6. So for the example 2, the input node has two levels. The input has two levels, node 1, 2, first level, node 3, the second level. So following the rule, we first visit node 1 and then goes to the child level, node 3. After visiting all the nodes in the child level, so we backtrack to the previous level and then visit node 2. So that's why the output is 1, 3, 2. And then in example 3, the input is empty list and then the output is also empty list. So how to solve this problem? So the idea is using DFS, depth first search. So why? Remember, for depth first search, we first go as far or as deep as possible before we backtrack. So in this case, let's say we first visit the child node, and then all the nodes like on the same level as the child node, and then also the child level. So basically, after we completely visit after we complete visiting all the nodes on the child level and then any child nodes, then we backtrack. So basically we first go as far or as deep as possible before we backtrack. So that's why we want to use the DFS, depth first search. So let's code the solution. So for that first search, we are trying to use a stack. So to keep track of the order of the nodes that we are going to visit. So we first check if the head is empty or not. So if not head, we just return head. So remember in example 3, if the input is empty, so we just return the empty list as well. And then after that, create a dummy node. So this dummy node is used to keep track of the head of the first level of the list. So basically, this dummy node is going to point to the head of the first level of the list. So the next node of this dummy node is the head of the first level of the list. We also have a stack. And then initially, we put this head into the stack. So we first visit the head. We also want to keep track of the current node and then also the previous node. So basically, every time we are trying to pop a node from this stack, and then the node popped from stack is our current node. We also need to know its previous node so that we can point previous node's next pointer to the current node, and then also point the current node's previous pointer to the previous node. So that's why we need to both keep track of the previous node and also check while checking the current node. So initially, previous node equals the dummy. So while stack we just pop, that's our current node. We pop the current node from the stack. And then we check, and then we start visiting the current node. We first check if the current node next is now none, then we put that into the stack. If current node's the child node is now none, then we put that into the stack as well. We are checking the current node's next nodes first, and then first put onto stack, and then we check the current node's child node and put the child node onto the stack. So in this order, we guarantee that we first visit the child nodes before we visit the next node. And then if this child node, let's say, also have the child node, so we continue putting the child node on top of that stack. So we are guaranteeing that we first visit all the child node before we backtracking. So in that case, after determining the next node to visit, we need to start point current node's previous equals the previous node. And then previous node's next pointer points to the current node. And then also current node's child should be none. After that, so we complete visit the current node. So before start visiting the next node, we should let our assign our current to the previous. So after checking all the nodes in the stack, so there is no more element left in the stack. So we just set, so our result is just return previous dot next. So that should be dummy dot next. So dummy dot next is the head of the first level of the list. But before returning that, we should set the dummy dot next, the previous from this dummy into a none, and then we just return dummy dot next. Let's try to run the solution. Okay, this solution is accepted. So basically the key idea for solving this problem is depth first search, because in depth first search, we visit or go as deep or as far as possible before backtracking. So here from the rules, the nodes in the child list should appear after current node and before current next in the flattened list. So here in this problem, we need to visit all the child node and also all the nodes in the child list and its child list before backtracking. So in this case, we need to use DFS. So using DFS, we use a stack to help us keep track of the nodes we are visit. So we have a previous node, and then we also have the current node. Every time we pop the current node from the stack, and then we visit this current node, and we check the current node's next node. If the next node is not none, we put that on top of the stack. If the child's node is not none, we put that on top of the stack. And then after that, we just do the assign the pointers. We point the current node's previous pointer to the previous node, and previous node's next pointer to the current node, and then set the current node's child pointer to none. After that, we complete visit the current node, and then before visit the next node, before popping the next node from the stack, we need to make sure that, okay, we also move the previous node. So we update the previous node. So now after visiting the current node, this current node becomes the previous node. So that's our solution.